Hi boys and girls. In the last classes you understood the different logic gates like the NOT gate, the NAND, the AND gate, the OR gate, inversion of that like the NAND, the NOR. In the end you saw the exclusive OR gate and exclusive OR gate. You understood the truth tables of these things. You verified the truth tables of all these gates with QX. You understood those waveforms. You understood the propagation delays and all that. Now in this video we will see the various properties of gates. So let me start with that presentation. First you will understand the learning outcomes of this video, and then you will see the associative property of gates, and then the non-associativity of NAND and NOR gates, then the universality of NAND and NOR gates, and finally we will summarize the properties. What you will in this video is that you will learn the associativity of AND, OR, XOR gates. Then you will learn the relationship between the XOR and XNOR gates. Then you will learn the universality and non-associativity of NAND and NOR gates. So these points are very, very important. Now first about the associativity of gates. As I told you, AND, OR, XOR, XNOR, etc. are associative. Like A and B and C, that is equal to A and B and C, that is equal to A and B and C. Okay. That is, if you look into this diagram, this is a two input AND gate. This output is, these inputs are A, B, and this output is A, B, A and B. That is ANDed with C, that gives A and B and C. So it says that you can make a 3-input AND gate by cascading two input AND gates this way. That is, you can make a 3-input AND with inputs A, B, C with the help of two input AND gates. You can cascade this like first thing takes A and B, then it is given to an AND gate with another input C. So that gives me A and B and C. So this is this AND is associative. Like OR is also associative. A or B or C, that is equal to A or B or C, that is equal to A or B or C. So what is this? It is as in this diagram, that is A or B, that is here, that is ORed with C gives me A or B or C. That means there is a 3-input OR formed by two input ORs. That is just by cascading two input OR gates, I can make a 3-input OR gate. Likewise, exclusive OR is also associative, like A XOR B XOR C, that is equal to A XOR B XOR C, that is equal to A XOR B XOR C. So I can make a 3-input XOR gate by cascading two input XOR gates. Similarly, the XNOR function, that's also associative. A XNOR B XNOR C is equal to A XNOR B XNOR C, that is equal to A XNOR B XNOR C. So these gates, the AND, the OR, the exclusive OR and exclusive NOR gates are associative. Now, but when it comes to the NAND and NOR, they are not associative. Like A, B all complement and C all complement, that is A NAND B NAND C, that is not equal to A B C all complement. That is, if I take a 2-input NAND gate and A and B all complement, this gives me A and B all complement. If I cascade with a second NAND gate with another input C, what you get is A and B complement and C all complement and not ABC complement. In order to make it ABC complement, that is to make a 3-input NAND out of a 2-input NAND, you need 3 NAND gates. Why? Because you take AB, this gives the first NAND gives you the output AB all complement. Then I have to invert it. What I can do is I can use another NAND as an inverter. If I told you this is A and A, whatever is coming here, if this is X, that is AB all complement. If this is X, then X and X is nothing but X. So output is a complement. So what happens is this shorter with this NAND with shorter inputs that acts as an inverter. So what you get here is AB. The input to this inverter is AB complement, and this is AB. So input to this NAND are A, B, and C. So what you get is A, B, C all complement. This is a 3-input structure. This is a 3-input NAND structure. So just by cascading two input NAND gates, you cannot get a 3-input NAND gate. Why? Because it is not associative. NAND is not associative. So likewise, A or B or C not equal to A or B. I think there's a mistake there. The overline has happened over both of this. This is A or B or C all complement. That's a 3-input NOR that is not equal to A or B all complement or C all complement. There's a small mistake here. You please correct that. So likewise here, if you want to connect if I connect a 2-input NOR here, and if it is cascaded to another 2-input NOR gate, you will not get a 3-input NOR. You have to connect a NOR like this. I have an A or B, then there's a complement, then there is a third NOR, then only it will work out. So that means what point we stress here is that NAND and NOR are not associative. That's a unique property of NAND and NOR. They are not associative gates. Now there is another unique property of the NAND and NOR that is called universality. That means that NAND and NOR are universal in the sense that all other gates and logic can be implemented with a NAND or NOR alone. So you can implement any other gate, any other logic circuit with NAND alone or NOR alone. So that's meant by the universal property of NAND and NOR. NAND and NOR are universal gates. Any other logic gate, any other logic circuit can be implemented with NAND alone or NOR alone. Okay. So for example, if you want to have an inverter, this I just saw that if you want to create an inverter gate or a NOT gate, with that you can connect a NAND like this with a 2-input shorter. This becomes A and A all complement. This is nothing but A complement. Likewise, if you connect a NOR here, A or A all complement, which is nothing but A complement. So this is the implementation of an inverter with a NAND. This is the implementation of an inverter with a NOR alone. Now what if I want to have an OR gate with a NAND? I want to have an OR gate with a NAND, because OR gate A or B is this. So what I do is first I take A, invert it with a NAND structure so that it becomes A complement. Here it is B complement. Then what I do is I give it to this NAND so that what you get at the output is A complement and B complement all complement, which by De Morgan's law it is A double complement or B double complement. A double complement is the same thing as A double complement is nothing but A, B double complement is nothing but B. So it is A or B by De Morgan's theorem. Now, how can you make an OR with NOR? It is pretty simple, because just invert the NOR and you will get OR. This is AB. This is A or B all complement, that when inverted with this inverter, this gives you A or B. So this is how you make an OR gate with NOR. This is how you make an OR gate with NAND. What I do here is A complement, B complement. This is AB, A complement and B complement all complement, which is nothing but A or B by De Morgan's duality theorem. Now, how do you make an AND with NAND? It is pretty simple. AND with NAND means this is A and B complement. Just complement it by an inverter that is made with NAND, so that this becomes AB. How do you make a AND with NOR? Just like I made a OR with AND. First I do an inversion. This is A or A complement, that is A complement, and this is B complement. So what you get here is Y equal to A complement or B complement all complement, which by De Morgan's theorem it is A and B. This is actually A double complement and B double complement, which is nothing but A and B. This is A complement, this is B complement, this is Y equal to A complement or B complement all complement, that is nothing but A double complement and B double complement by duality theorem. A double complement is nothing but the same thing, that is A and B. So this is how you make an AND with NAND and NOR. Now what about an XOR gate? XOR function is nothing but A or B and A bar or B bar. So This circuit realizes an XOR gate. This is XOR using NAND. So if you look here, this is AB. This is AB all complement. This is with one NAND IC. I can do this with just with 4 NAND gates. I can create an exclusive OR circuit. How do I do this? First, I invert this. I take a NAND of A and B, so that this is AB all complement, which is nothing but A complement or B complement. Now this comes here. This A comes here. This is nothing but this A is ANDed with this A complement or B complement and taken a all complement, so that it is A and A complement, which is 0. Then A and B complement. Okay. A and B complement, all complement, which is nothing but A complement or B. That is what you get here, A complement or B. I will say these steps again. This is AB and this is AB all complement, which by De Morgan's law it is A complement or B complement. Now this is ANDed with A, actually NANDed, ANDed and inverted. ANDed with A means this is what comes here is A complement, which is 0, forget that term. Next is A and B complement, okay, all complement, okay, because there is an inversion here. A and B all complement is nothing but A bar or B. Likewise here it is NANDed. This A bar or B bar is NANDed with B. So when I AND B with B complement, it becomes a 0. Then it is a B A complement all complement, that is B complement or A. Now these two things are ANDed and taken. So when I AND this, it is becomes AB or A bar B bar all bar, which is nothing but you can do some little computation here and you can see that this is AB complement or A complement and B, which is nothing but my exclusive OR circuit. Now, how do you make an exclusive NOR out of this? You need one more gate here, because you want to make it A, B or A bar, B bar. Okay, exclusive NOR is nothing but A and B or A bar and B bar. So you have to remove this this overline, this complement to make it an XNOR. So you connect one NAND here as an inverter and that will become an XNOR thing. You can try all these things with the cubes. Now, before I proceed with this, when I say cubes, I will show you some simulations. Before I simply proceed with this class, I will do some simulations. Let me go back to this simple things. First, I will see. I will see some simple simulations. First I will see NAND, an XOR with the NAND. This is a circuit. This is a circuit we just discussed. Okay, this is a circuit we just discussed. This is this point is AB all complement. This point is AB bar or A bar B. First we will run the simulation and we will see whether this is giving me an exclusive OR result. So if you look here, you can see that you can see that the truth table is that of an exclusive OR. That is Y is my output and A and B are my inputs. So you can see that this follows this is 0 exclusive OR 0. This is 0 1 1 1 0 0 1 0 0 1 0 0 0 0 1 1 0 1 1. For when it is 1 0 and 0 1, the output is a 1. So this is the this is an exclusive OR circuit. This is an exclusive OR circuit. Now, if I add one more inverter, it will become an exclusive NOR, and we will see the associative property, the associativity, the non-associativity, etc. Whether the NAND is associative or not, we will see. This is one circuit that see, this is these are NAND gates. This is a 3-input NAND. What is the function here? It is ABC all complement. What is this? This is the cascaded two NAND gates cascaded. Now I have to show that this does not follow associative. That is, this output Y and this output Z should be different. Okay, because this is ABC all complement. This is not ABC all complement. It is AB complement and C all complement, which is different from ABC all complement. Now I will run the simulation and you can verify this. Now you can see that this is ABC and this is ABC, and this is my Y and this is my Z. This is the ABC whole complement. You can see that only when these three are high, no, this is a NAND. This is a 3-input NAND. So if all these values are 1, so when all these ABC are 1, this goes 0. Okay, this when one of the input is at 0, output is at 0. When all inputs are 1, output goes to a 0. That is the meaning of a NAND gate. If at least one of the inputs is at 0, you can see that from here to here, that is up to 7 nanosecond. You can see that one of this input is always 0. So that means Y remains at high. And when does it go to 0? That is when all the three becomes a 1. That is from 7 nanosecond to 8 nanosecond. This goes to a 0. Okay. Now this is a different thing. This Z is, you can see that this Z, which is a cascaded, that is the output of two cascaded NAND. That is different from my 3-input NAND output, which is Y. So Y and Z are different. So you can see that that I have verified that NAND is not an associative circuit. Now let us see whether NOR is associative. You can see that this NOR. Here also I have a similar setup. Only thing is the gate is different. It's a NOR thing. Now you can see that these two things are different. This is a 3-input NOR. This is A or B or C all complement. This is A or B, that is ORed with, that is NORed with C. These two are different. A or B. This is not A nor B nor C. So I can run this simulation. So I have taken these three signals and connected in parallel to a 3-input NOR gate and this cascade, and I have to verify, and you have to compare these outputs Y and Z. So I come here, I simulate this. You can see that this Y is a 3-input NOR, because you can see that this is high only when all the three are low, all the three inputs are low. This is the only place where, this is one place where all the three are low. I will make it a little bigger. Okay. You can see that here these are here this is low. Here also all the three are low. That is why this NOR output becomes high. Here if you say one of this is always high, one of the three signals is always high, so that means the NOR output is a low. Okay. Now this Z is not a 3-input NOR. It is just a cascaded version. A NOR is cascaded with a 2-input NOR is cascaded with another 2-input NOR. It is not a 3-input NOR. So this Y is a 3-input NOR. This Z is different from Y. Now I have demonstrated with cubes that NOR is not an associative circuit. Now I'll go back to my presentation. Now you have seen how an exclusive OR gate is made with a NAND. Now let us see how an XNOR gate is made with a NOR. XNOR gate with a NOR. This is XOR with a AND. This is XNOR with a NOR. I told you this is this thing is AB or A complement and B complement. So here it is what you get here is AB. This is A or B all complement, which is A complement and B complement. So what comes here is A, and this is A complement or and B complement. So what comes here is A or A bar B bar, which is nothing but A or B bar all complement. I told you this theorem in the last class. A or A bar B bar is A or B bar, okay, with a complement at the top. This is nothing but A complement and B complement by De Morgan's theorem. So everywhere I am utilizing this De Morgan's theorem, so you have to understand it very thoroughly. So this is A bar B bar and this is B. So this what goes out is B or A bar, because B or A bar B bar is nothing but B or A bar. B or A bar all complement, which is nothing but A and B complement. Now this is AB AB complement or A and A bar B all complement, which is nothing but AB or A bar B bar, which is an XNOR. Now if you want to make it an XOR, I have to add one inverter with the NOR, and that will do. XNOR using NOR. Now I can demonstrate that to you. This is XOR with the NOR. Okay, these are, is it a NOR gate? Yeah, that's a NOR gate. Okay, now what I connected is this is an XNOR circuit. Now I have to simulate and verify whether it is an XNOR circuit. Now you can see that this truth table shows that it's a This truth table shows that it's an XNOR circuit. When A and B are both 0, 0, when they are equal 0, 0, 1, 1, it becomes a 1. When they are different, that is 1, 0, 0, 1, it is a 0. This is a complement of the two input XOR. Here you can see that when both are equal, like when A and B are equal, its output is 1. If they are different, it's a 0. Okay, when it is 1, 0, it's a 0. It's 0, 1, it's a 0. When it is 1, 1, it is high. When it is 0, 0, it is high. So this now I have realized an exclusive NOR circuit with a NOR alone. So I have demonstrated the universality of NAND and NOR gates. Now let me go back to my presentation. Now let us summarize these properties. The De Morgan's theorem, it says that if this is A and B, A and B, it is A or B all complement. This is nothing but A complement and B complement. This bubble indicates a complement. This is A, this is B, this is whatever going into this AND gate is A bar. This is B bar, A bar and B bar. What is that? That is equivalent to A or B complement. Likewise here it is AB all complement, A and B all complement. That is equal to A bar or B bar. This is A and B going in. There is a bubble here. This bubble shows an inversion. So this is A bar or B bar. Now you understood that AND, OR, XOR and XNOR are associative gates. I demonstrated the associative property with the Qs. Now NAND and NOR are not associative, but they are universal in the sense that any logic can be developed using NAND or NOR alone. So that also I have demonstrated. I have demonstrated that I can make a AND OR inverter, exclusive OR or exclusive NOR with a NAND or NOR circuit. Okay, of course you can make a NOR circuit with a NAND and a NAND circuit with a NOR. That you have already seen. Now what happens is, this is a NOR gate. This is a noted AND. This is followed by, put one more bubble here, and it becomes this is a NOR gate made with a NAND. So here this you put a bubble here to make it a NAND. Then you do one more inversion. So you understood that this property of NAND and NOR is very important. There are two cardinal properties of NAND and NOR. One is they are not associative. Second, they are universal. They are universal gate. NAND and NOR are universal gate. NAND and NOR are non-associative gates. Okay. Now NAND and NOR are complements of AND and OR respectively. It's always, whatever be the number of inputs, NAND is a complement of and NOR is a complement of OR. But exclusive OR and exclusive NOR are not complements, not always. If they are 2 input or 4 input, they are complements. Like A XOR B is the complement of A XOR B. Okay. If these inputs are 2, the like A and B, 2 inputs are there, A exclusive over B, that is the complement of A XOR B. Okay. But A exclusive A XOR B XOR C with a 3 input, with odd inputs, that is the same as A XOR B XOR C. Many people do not know this. Many books make the mistake that they assert that exclusive OR and exclusive NOR are complements. They are not always complements. When the inputs are even, they are complements. When the inputs are odd, exclusive OR and exclusive NOR are the same. Now, you can make a 2 input XOR can be used as a NOT gate. Like one of the inputs is held at high, this A will come, this will be A and 0 or 1 and A. So 1 and A complement. So you will get A complement here. This is one way in which you use a exclusive OR as an inverter. Okay, this is sometimes this will become useful to you when you do counter circuits etc. on board. This thing will become very handy to you. If one of the input is held high, this inverter, two input exclusive OR works as an inverter. Now this property, you know, like A XOR B is a complement of A XOR B. This property number 10, I will demonstrate with a Qx code. That is, a 3 input XOR and 3 input XOR are the same, but a 4 input XOR and 4 input XOR are complements. So if the inputs are odd, they are same. If the inputs are even, they are complements. That I will demonstrate with Qx. Here this is an exclusive, this is a 3 input exclusive OR gate, this is a 3 input exclusive NOR gate. We will prove that Y and Z are the same. I have 3 switches, S1, S2 and S3. This is, I'm sorry, not switches, I'm sorry, signals. I'm sorry, signals. Signals S1, this is 1 nanosecond, 1 nanosecond, this is 2 nanosecond, 2 nanosecond, this is 4 nanosecond, 4 nanoseconds. So that I will get a neat truth table. Now I have done the simulation for a truth table. You can appreciate this truth table. Now you can see that this these are my ABC inputs. This is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So all available patterns of ABC are available here. See, if you see that this is a 3 input XOR, that is 0, 1, 1, 0, 1, 0, 0, 1, and this is 0, 1, 1, 0, 1, 0, 0, 1. Now I have demonstrated that the two are equal. When I have odd number of inputs, exclusive OR and exclusive NOR are the same. If the inputs are even, exclusive OR and exclusive NOR are complements. So if somebody asks you whether they are complements, never say they are complements. Exclusive OR and exclusive NOR are not always complements. But NAND is a complement of AND, OR is a complement of NOR. But exclusive OR and exclusive NOR are not generally complements. Hope you understand these subtle points. Now what you learn in this video is that you understood the properties of logic gates, and that's the end of this video. I thank you all.